All right. Good afternoon, everybody. Um, I'm gonna share my slides. I've been working on some stuff that I think is kind of special for you guys. I hope it works. Right. So my name is Dirk Englund. I'm a professor of electrical engineering and computer science here at MIT, and I'm joined today by Dr. ChaohanCui of the University of Maryland, who has been helping me with some of the course material and to keep me on track, um, uh, which has been kind of difficult given the um, the goals I set to myself. But let me show you that as we go through. So I will. My intention here is to uh, divide these 2 hours into the following blocks. First, I want to give you some background into where quantum networks fit in this emerging technology space of quantum information science and technology. And um, and along the way of even that introduction, define the physics that we will need to be able to go deeper into the subject matter. And my hope is that you will, if you're not familiar with quantum networks, you will have some you will leave these 2 hours that were allotted with some appreciation for the machinery of quantum networks, and then also, my hope is to give you some sense of how useful they could be and where they come in, and encourage your questions. And here I also Chauhan is also very happy to and has volunteered to take questions along the way. And if there are questions that he deems should be publicly, if there are very questions that would be interesting for the whole group, then he will elevate these and we can talk about them together. I like the more interactive style than me just talking to the computer. So please bring your questions. That makes it much more interesting and much more fun for me, and hopefully and hopefully also more rewarding for you all. Um, and so we have 2 hours, and I will. And Chauhan has agreed also to keep track of time so that we can take a break every 30 minutes or so, which again will also I'll stay here, but yeah, people might have biological breaks and whatnot. But I'll stay here and take your questions at that point, that are maybe like overflow questions from the previous half hour then. Um, and the other thing I want to do is show you really the machinery of quantum networks by giving you the code and the simulation tools to that are used in practice, at least at different levels. Like some of them are on the physical layer, others are in the algorithm layer. And to this end, I have put together some resources that comprise um, sort of PhD level, I would say, tools that are used for quantum optics and in particular quantum network simulations. These can be kind of tedious if you're not familiar with them to learn. And so I've also equipped these tools with an AI tutor, um, that I think is actually becoming quite helpful. And here I want to give a shout out to the CQN, which has supported me in advancing this, what I call a chat tutor, over the years. Um, and well, I really through forums, just to a forum like, hey, let's try this out in this forum or that. And so this is so there's a history there with this chat tutor for CQN, and I'm glad that I think that this is working a lot better than it did early on. when I rolled out the first chat tutor, it was just after the release of GPT-3. Now we have GPT-5, and it's not even using GPT. It's increasingly for me, using local models that I run here at MIT. All right, so that's the sort of overview. Now, where are we in context? So you have these general purpose computers, like the computer in my phone, or how we're speaking today, the CPU, a general purpose computer. But along the way, it emerged that specialty computers can dramatically improve the overall system performance. And one is graphical processing units, which increasingly we use for all kinds of other things. By the way, plug here for this is a pretty cool computer. And so that's a specialty computer. And there are other specialty computers, like quantum computers, that may also prove, although it hasn't yet been the case, but there are a lot of excitements about this additional paradigm for specialty computing that would augment the power of conventional computing systems by allowing you to offload some computations that are particularly difficult for CPUs and GPUs onto this different computing paradigm. Just like GPUs are used to offload specialty computing like matrix processing from a CPU. And so, yeah, there's been a lot of advances in this field. And in fact, there's a close connection to quantum networks, because if you have a quantum computer, then that's useful. You will, like what people did at the beginning of the internet, different people will want to use it. And maybe you want to be able to combine the power of two quantum computers or more than that. And so very quickly you say, oh, if a quantum computer is useful, then a quantum computer that's networked will be especially useful. And there's an argument that for quantum computers, that may give you an exponential improvement in the compute performance if you measure it, for example, by quantum volume, provided that the interconnects, the network that links these quantum computers, is of sufficiently high reliability, that the error rate between two quantum computers is sufficiently low. And you may need error correction, entanglement distillation, and other methods to make these links very high fidelity. If you have that, then it becomes possible to improve the performance of two separate quantum computer beyond the sum of the parts. And the other area of really the renaissance in computing is in machine learning. And machine learning is super important for controlling quantum computers and quantum information science and technology systems. Like, for example, in detecting a syndrome measurement of a error correction algorithm. A syndrome is like a flag, like this is the type of error that occurred, and let me correct it. And these syndrome measurements are a type of detection that in machine learning is called perception. So you could, as the machine becomes more and more complicated, or maybe the physics is not entirely known to you and so on, you can optimize the type of filters you apply for syndrome detection. And so that makes a natural link to learned filters, like in autoencoders. And there you are already getting into deep neural networks. And the beginning of the machine learning and AI revolution that we find ourselves in. So machine learning is useful for controlling and measuring quantum computers. It may also, and I think it's fair to say it is also very useful for building and designing quantum computers in maybe not so much in perception, but in the more recent flavors of AI, like generative AI, and maybe most importantly, physical AI. So in this talk, I found both of these topics super fascinating. And in this talk, I'm trying to you will see a combination of these two at play. But the area of focus for us is going to be in photonic control. Now, photonic control, I just showed you an example where photonic control is where in the networking of quantum computers, uh, if they're relatively far apart, tens of meters or so, then optical interconnects are particularly useful. Fibers are great, and so forth. And so optics is a consequence. The utility of optics is a consequence of the desire to network quantum computers. And we see this in this diagram here, where in quantum networks we have memories that may be far separated. Maybe they're in a data center, maybe they're spanning, a city, maybe they're spanning a continent or even the globe or beyond. And these are here they're simplified. I represent them here as a spin, where an electron spin, for example, could be spin up or spin down with respect to an applied magnetic field, representing a binary 0 and a binary 1, respectively. And but this is a generalization. Really, it could be in reality. There's going to be some sort of an error-corrected quantum bit or qubit, and so don't take this literally as just being one spin. This will really be a collection of quantum memories of some sort, actually running some closed loop algorithm for error correction, so that the memory coherence here stays long. And then you want to connect these. And so one way to connect them is to establish these optical links between them. And one way in particular to implement all of this together is to use atomic systems as the memories, which again, electron spins and nuclear spins and so on could be convenient and are convenient local memories that can have long coherence times of milliseconds up to, in some cases, hours. And to link them via optical channels. And the color frequency of these optical channels is largely dictated by the atomic transitions of the atomic memories, because that is how the interface, the atom is an interface between the electrons that are in their outer shells and the optical field by the resonant interaction between the electronic transitions, and the optical fields. So it turns out that a lot of the time, for most widely used quantum memories, these transitions are in the wavelength range between, I don't know, under 1 micron or so in wavelength. So for that reason, oftentimes people then do frequency conversion to be able to bridge into optical fiber. So there would be another element in there, which is not shown here, that's the frequency conversion element. All right. Now the thing is that these optical links are lossy. So if you launch a photon from an atom through an optical link, the probability that it will arrive on the other end is pretty small. And we said we need high fidelity. So we need things to work all the time with 99 point, really like 99 point something, maybe 99.5% success rate. So lossy fiber links won't work. And so we need a way around it. And so the surprising answer to this the answer to this has turned out to be that you can first establish entanglement between links, between memories via the use of a link. And this establishment is some sort of a heralding signal, like what we were talking about earlier. The syndrome measurement is some heralding signal, some measurement pattern that tells you, okay, the desired state has now been prepared. And once you've prepared it, then you can use this entanglement as a resource to teleport states or to teleport directly gates between quantum memories at distance. And that allows this network of memories to, if you also, if you also have the other necessary ingredients, which include good 2-qubit gates, which are often done locally, then what you have is a fabric that serves as a general purpose quantum computer. And it happens to be in a network. But really, ultimately, what this comes out to be is a general, if you want error corrected, long distance uh, um, links, then you come very close to a general purpose quantum computer. So therefore, it's useful to look at other types of quantum computers and to see how optics plays a role there. Here I'm showing you an image from a laboratory of my collaborators in some work, Mikhail Lukin, Vladan Vlutic, and Markus Kreiner, um, uh, um, uh, that positions ultra-cold atoms, in this case made of rubidium, cooled to microkelvin temperatures in vacuum, into arrays of atomic systems, where again the internal state represents a qubit. And here the interactions are realized by atomic physics methods, like dipole interactions. But at longer distance, still, there is a strong desire to network them via flying photons. And then you have this kind of a quantum computer or networks of such quantum computers that are storing information locally. Ditto for trapped ion systems. You will stick these into these memory cells, and then you still want to connect them. And I could go on about other kinds of quantum computing platforms, but a common thread is that if you have a quantum computer that's useful, it will become more useful if you can network it. And so this is really one way of looking at the demands of a quantum network. Like, what should it do? How well should it work? And so on. Well, it should enable you to make two quantum computers more powerful than the sum of the parts. That's a useful quantum network. Okay, and it implies something about the fidelity of the optical links and the whole architecture and so on. That is a way of measuring if a quantum network is useful. But I'll get back to that utility question in a moment. But this is essentially, I think it's a good way to think about the problem. So we're going through the introduction here, and I think I'm going to skip over that. What I will skip over this link here because we'll get to that in a moment. But so the outline for the course is we'll go through a higher level overview of quantum networks, the theory, the applications, the devices, the protocols, and then I want to dig into the code and give you the tooling by which you can explore questions like, would this link be useful? What is the rate of entanglement generation between randomly selected nodes in a network? Are two quantum computers, one network, better than if they're not networked? These kinds of things. I want to give you the tooling for that so that you're equipped to explore some of these questions on your own. So, or with the chat tutor at least, with an AI tutor. And so here I have, at this point, I'm already going to share with you some of my notes. So first off, I shared with you the slides, and for people who might have come late, I'm going to do that again. And there we go. So these are, once again, the slides, and you can click on the slides and you will find a link. So here.
So Dirk,
Yes.
we need the host to pop this link to the audience.
I just sent it to everybody, so everybody
Okay.
should receive it
Ah,
now.
Great.
All right. I see lots of little icons popping up. Very good. There you are. Hello. Wish you could see faces, but all right. So maybe everybody could just take a moment, click on this link so that you have it open in another tab. Ah, and I made a mistake here. Look at that. Uh, this should be Chauhan and Dirk, and it is the previous instructors and Dirk. Um, so in defense of Prajit and Chuck, they did not collaborate. They did not contribute to this. And um, so yeah, this is, I'll update this. But what I wanted you to get to is here. So we're going to get into this material. So hopefully this works. All right, it works. So I pushed this content of lecture notes that I prepared only for you all um, in a program called Marimo that I'm really like a lot. This is like a IPy notebook alternative. And here's the first chapter. And you will have these notes. And you can ask these notes questions. Let's see if that works. Yeah, okay. So let's see if this works. I really have not tested this on the latest deployment. Okay, good. So let's see. It's a bit slow. This is because it has knowledge of the whole database. Okay, so it's pretty, I think it's pretty useful. I found other people have told me this, they find it useful. So here, how do I calculate? I don't know. Let's see what. So here's a point that we're going to get into in the theory after this introduction. But again, people who are familiar with this subject matter may already want to wander into the more technical stuff. Uh, is that one assumption we make in describing the optical channels I showed on the previous slide is that the thermal occupation of photons of these optical channels is zero. And the justification for that comes from this derivation here. So the thing is that the photon energy of at a telecom wavelength, for instance, is about 40 times beyond the thermal energy of, wait 1 second, is above, is 40 times above the thermal energy um, at 300 Kelvin. And because the ratio of the optical frequency and the thermal energy at 300 Kelvin appears here in the denominator, in the exponent of the denominator of the mean photon number according to the Bose-Einstein distribution. If you plug in the numbers, 1 over e to the 40th power minus 1 is very close to zero. So this is why we're allowed to make that assumption about for describing our optical channels. But would the description that we're going to use for quantum networks apply if we were working, let's say, with microwave fields, like with radios, like our cellular phones? What is the mean photon number? This is of an optical mode. We'll get into that theory more later. What is the mean photon number at a carrier frequency near, you know, cell phone frequencies, 2.5 gigahertz or something? Okay, so you can, so it will give you a good answer. I'm pretty sure I've tested this kind of thing before. Okay, we don't have to wait. So this is something that you could already. Here we go. Okay. So, oh, look at this. So this assumption that we make at optical frequencies to describe our quantum network channels, right? That the mean photon number at optical frequencies, if you run this, is zero. Well, it's not. It's certainly not the case at microwave frequencies, right? So this I think is a nice way to explore that, and um, so yeah, I encourage you to play with this. Now, it turns out that there's a problem. I couldn't get this to work with everything that I wanted in this deployment, as nice I think as it is. And here you see QPD tutorial. You can take a look at how the QPD tutorial turned out. The problem is that in the environment here on Vercel, I could not install, I could not get Qtip to run. And there's a way to get around it, but it was turning out to be very tedious. So for that reason, I've actually I'm trying out something different for you so that we can actually together run some of these notebooks interactively to enable yeah, basically quantum optic simulations to run. Um, and and so I have, let me see if I put the link in there for that as well. Yeah, I have the link. So if we go to the next slide, you can see here a link. Now this is another little project that I've been working on, and you should be able to see, you should be welcomed by this, what's called Open Web UI. This is a interface, an open source interface to AI models. And I use it here to be able to work on these notebooks with you. So in this installation, which I have set up here at this URL, you should be able to register. Now, let me just check if that's the case. Do you guys see my screen, by the way, Chahan?
Yes, yes, I
You
can
see
see
this,
the
okay?
screen.
Were you
Yeah.
able to get an account? Can you try?
I Let me turn on this because previously I don't have the account. Let me
Yeah, no, you don't.
Yeah,
Just I just set it up basically.
register one. Okay.
So yeah, you should be able to take your O off and see, suppose I use this. Now there's a bit of a bug here, but if you just press on it again, it should work. There we go. Okay. Um, this is all right. This system will allow us to actually run deployments using the tools, because in here I have my Remo notebook tool, which is running on my own servers, where I have naturally, as any good quantum optician, installed Qtip. And you can thus use that environment for running it. Okay, so that's um, that's that. So you can take a look there. So we'll get back to that later.
Yeah, I can log in. I can
You
log
were?
in.
Okay,
Yes.
cool. Very good. And all right, so now uh, I will continue with the introduction. Um, and maybe at this point, it is now 30 minutes past. So I thought, right, so we can take now a 5-minute break, stretch and so forth. And I'm happy to take some questions already. I'm going to turn off my screen share, and I'd be happy to take some questions if there are any.
If you have questions, you can put in the Q&A box.
I'm also curious where people, what your background is. Are you like, this is why the CQN team told me to do surveys. Now I realize why. Very cool.
If you want, I
But
can open a fill in the blank.
oh yeah, that would be fun. Yeah,
Okay.
love to see my who's their audience.
Okay. I just launched one. Was there anything specific you'd want to ask?
Yeah, I'd love to just ask let's say, what is your field of study and what stage are you in? Are you, let's say, physics, undergrad, physics, grad school, computer science, grad school? Uh, are you working in industry? Anything like that would actually be quite interesting. I guess, does it have to be multiple choice?
There is a question in the Q&A session about, is there any library working with MATLAB?
Oh, yes. In fact, actually, that was the tool I used in yeah, there is a MATLAB library, and what's it called? So MATLAB, Quantum Optics Toolbox is actually a very nice package. Quantum Optics Toolbox. Any other questions?
Let me see if I could view those responses. Somebody from our chat said they're undergraduate systems engineering, or that's their field of study. Somebody said I am a senior applied math and CS undergrad at UMass. Another person said, hi, I'm a graduate student working in quantum optics at UIUC. I'm about to graduate, but these seminars are a very nice way to polish my knowledge from time to time. And then somebody else said, engineer at quantum networking startup.
Wonderful. Um,
And then I think I'm gonna open another poll since a few people left for the break, probably. And then I'll just leave this one open for a few minutes.
okay. All right, let's take one more minute and then we can resume.
Here's a general question for you, Dirk. There was an undergrad if you, in computer science want to know that what students should focus on if they want to be success in next 3 to 5 years in the quantum uh, engineering subject.
Yeah, so I think computer science is certainly useful. I um I've been really consumed by CS questions. It's such a great tool for better understanding, I think, quantum systems, because you can simulate them. So really, I think a really sort of a sea change that's underway is that the conventional sort of textbook learning um, can make room for or be augmented by, I would say, actually textbook learning is really good. It gives you the foundation. So this kind of like quantum optics that we learn here, the principles, this is a compact model of the world. It's compact. We can calculate a lot of things in quantum optics to high precision. It's sort of a luxury. Um, but when you build systems, inevitably the system becomes more complex, and to then make predictions about how a system will behave requires more extensive models than the tooling that you get in a quantum optics course. And so for that reason, computational methods, such as building physics-based models of experiments that include not just the physics, not just the optical fields and perhaps some beam splitters and so on, but also the apparatus, right? The table they're sitting on, the signal processing that happens, the analog to digital converters and so forth. These things become very important to understand how the machine altogether works. And the problem there is that even though this is well known, right, and large companies will have large teams that are dedicated to modeling their products, and just even the verification teams can be quite large. But you can't do that yourself. So one always had just a small glimpse of the big picture. But where I think these AI tools come in, and what actually prompted me, for example, to start a company with some of my colleagues called Axiomatic AI, it makes it possible for you to model complex systems even as an individual. So you don't depend on being in a team that has, dozens of specialists for different fields. You can do a lot by yourself. And that in turn gives you much greater insight, I think, into the physics and the apparatus that explores the physics. Now, when you think about what degree is a good one, I think anything that allows you to be more precise in predicting physical systems is really, really useful. And that includes, modeling of, systems using physics-based methods, so computational models, data-driven models also, so machine learning aspect there. And if you're in physics, or applied math, of course, good example too. If you're in physics, then use these computational tools that now with Cursor you can get a long ways to building good models of the physics of the system as well as the algorithms that control it. So that's what I would say to that. Okay, so I think we're gonna move on. So I'm gonna just return here to this. So 1 second.
I also got a few responses from our poll, but we can read them for the next break if that works for you.
Okay. Yeah, let's leave them for the next break. I think we have had enough. This has been about 15 minutes, 10 minutes about. All right. So now turn on my screen share again. Where did this thing go? Here. Okay. Yeah, so before the break, I was just sharing with you this AI system here that has an integrated interpreter for running our Q-tip notebooks, and this resource here that doesn't have that interpreter, but I think it's nonetheless very useful. This has the slides. This has the lecture note material in it in a way that this AI can understand and help on to some extent. All right. So okay. So before that, I was saying we're going through an introduction, and then we're going to dive deeper into coding examples for quantum mechanics, for quantum key distribution, for a kind of entanglement generation technique that has proven important for example, for quantum network altogether, and is used in the Center for Quantum Networks, called the Midpoint Source protocol. And we'll have a coding tutorial for that. And then at the end, give you some we'll hand you off to a different tutorial that comprises many of the things that I've talked about here in one unified framework that is called QREP. This is something my team in particular, so my former postdoc and now professor at Stony Brook University, Dr. Choi, and I have worked on with a team of people at Delft University for building for quantum network simulations. QREP. We'll close with that. All right. So quantum networks. Essentially, we said the value of a quantum network is based on the added utility that it enables when you connect local quantum resources. So, for instance, maybe Alice interacted her magnetometer, which let's say happens to be based on an electron spin system in a diamond hydrogen vacancy center. And so she has the state, and this state has some information that is conditioned on the environment that Alice was in. And so maybe you'd like to make a measurement of the magnetic field difference between Alice here and Bob elsewhere. Now, there's a conventional way to do that is you measure the magnetic field locally by projecting, again, if it's based on NV spin systems, the NV spin into a particular state. And then you do that again on Bob's side, and then you send digital information from one to the other, and you take the difference, and that gives you your gradient. The downside from that is that when you project the state locally, you incur some spin projection noise. Okay. And that really is the limit of how well you can make measurements, is the projection noise of the quantum system that you use for that measurement. And if you have the ability to take that state for Alice and somehow get it over to Bob, so you can make a local measurement that you can design to take the difference, then you measure the difference directly rather than measuring two values and then taking the difference. And that has a fundamental advantage in having lower added noise. That measurement, the gradient, has lower noise than if you measure it twice and take the difference. It's just for Poisson statistics, for example, a square root of 2 difference. Now, square root of 2 is not so great, but if you have many of these, then that can matter for more. Or even if you locally measure many, and you'd like to maybe have a large entangled state, you can actually have an order n improvement. And so measurements are one application, and we see the utility there of why people would want to connect states that have some knowledge of the measurement of the environment, and why they might want to transport them around on a network. But like we said, there's other applications like in quantum computing. Quantum communication, of course, has applications in unconditionally secure communications, and so we'll explore some of these with examples. But just to lay the basis here, let's take a look at one of these, and I'm going to look at the simplest application of a network enabled by some means of having distributed entanglement. In particular, let's suppose that we have Alice and Bob have a share 2-qubit state that's initialized as a Bell state. And I now see that so there's different Bell states here. I'm gonna this is not to be confused. This is a slightly different Bell state. They're equivalent. But here, let's just start with a Bell state of either Alice and Bob both have a state 0, or they both have a state 1. So the Bell state in this case is 0 for Alice, 0 for Bob, plus 1 for Alice and 1 for Bob, or it could be minus, and that's 2 of the 4 Bell states. The other 2 are the plus minus superpositions of these states down here. And so what happens is if there's some means of having distributed this entanglement between Alice and Bob, then we can use this pair of qubits here, these lower pair, as a resource to teleport that state that Alice desires to teleport over to Bob. How? It's actually a pretty simple circuit. So let's take a look. So here Alice, what she does is that she applies what is called a Hadamard gate, which is a rotation of the qubit. That puts it into an equal superposition of 0 plus 1. So this thing here at the output gives you, in this case, 0 plus 1 all over square root of 2 to make sure that your probabilities are always summed to 1, are always normalized. All right. Subsequent to that, sorry, this was, I should have said, all right, sorry. Actually, here I have 2 steps. So in the first step, we assume that Alice has 2 qubits and Bob has 1 qubit, and they're initially unentangled. The first step here is the preparation. So then Alice applies a Hadamard, and then by some means, and this is, for example, in our case, implemented by an optical field that connects the 2 electron spins, there is a logic gate applied, C0 gate, and that produces an entangled state between the 2 of them. And subsequently, then when you have this resource here, you can Alice can make a measurement after this preparation step, and conditioned on the measurement that after a local gate between her 2 qubits, she measures the unknown state to her psi. And that will give an unknown, unpredictable measurement outcome. I'll give you 0 or 1. And you pass that information 0 or 1 over to Bob, and you do the same with the second qubit that Alice has. So after this preparation, she, in this interaction between her memory qubit and the resource qubit, she measures the resource qubit also, and passes that information also on to Bob. Now these values here, M0 and M1, they're either 0 or 1, they're binaries. And then if M1, for instance, is equal to 0, then x to the 0 is applied, which is the identity, and ditto for M0. So in other words, conditional on the measurement being a 1, Bob will apply an x or a z rotation on his local qubit. And somewhat magically, what happens after this measurement and this feed forward is that Bob has a state that is the original state that Alice had. Alice never knew what the state was, but after this set of operations here that generates entanglement, then does some local connection between the memory qubit and the resource qubit, and then measurements and feed forward, Bob ends up with that qubit. So this is how you can teleport an unknown state, unknown to the sender state, to another destination in the network. And you can do the same thing for all the possible input states, and then you can convince yourself that that makes it possible to teleport gates. You can have different ways of you can apply logic gates far away across the network. And that in turn allows you to do quantum computing. And so this allows general purpose quantum computing provided, like with any other gate in quantum computing, that the fidelity of the gate is sufficiently high. Okay, and so this I think allows us to see how these 3 main application areas are implemented: sensing and metrology, quantum communication, and distributed quantum computing. Let's take a look at how, in particular, this is implemented in the physics of atomic systems, and in particular in color centers and diamond. What I'm showing you here is one type of color center. This is here a nitrogen vacancy center. So you have diamond, carbon lattice. You pluck out two of the atoms and you replace one of the holes with a nitrogen atom. The nitrogen atom here is small enough that it will select one of the two places. It will either sit here or it's on the other side. And this asymmetry of the inversion properties of the nitrogen vacancy center, we'll see is sort of a problem. And the reason why in these kinds of networks, nitrogen vacancy centers, although they were the dominant memory type initially, are nowadays rarely used. But they're nice. It's a really good memory system and it's good for illustration. So what you do is, so we want to generate this this entanglement at distance. So what we can do is we can apply an optical field that is resonant in a spin selective way between the scatters depending on the electron spin state of the nitrogen vacancy center. In one spin state, the optical field doesn't interact with the optical transition. And in the other spin state, it does interact with the optical transition of the color center. And this is why when you reflect an optical field from a atom, or you have some optical interaction with an atom, you can entangle the optical field with the internal state of the atom. All right. Now this optical field here is entangled with the atom that it leaves behind, and it's traveling down, let's say, this waveguide. And you do this again a second time on Bob's system. And then you can send them through a beam splitter. The beam splitter can either reflect this optical field here and cause a photon to be registered on this detector, or on the other side. When you measure, you don't know which of the two photons here was emitted by or scattered by the atom, but you know that one was scattered by the atom. So when you detect a single photon. And this allows you to say, oh, okay, the system is in this case, a coherent superposition of dark, bright, or bright, dark of the two systems here, A and B. Now, the trouble with this is that there's a high chance, like most of the time, if there is a photon scattered or emitted from one of these centers, that it will be lost in transit or not detected by other inefficiencies. And so what could have happened and would also lead to a single click on one of these detectors is that two photons were emitted and one of them was lost. That's very likely. If you have a single photon detected, it's very likely that, in fact, two photons were scattered and only one arrived at your detector. So how do you prevent that error channel? Okay, what you can do is subsequently, after getting the first single photon click, you apply a pi pulse, you flip the spins from dark to bright and bright to dark for both of the emitters, and then you repeat the process. And if you then get a second photon detected, then it's a high fidelity heralding of this particular state. Let's see why. If suppose that it was the other manifold where you had bright, bright, then if you apply a pi pulse, you'll have dark, dark, and the probability that you will get a click in one of the two detectors will be very low. So you see this two-step sequence, which is called the Barrett and Koch protocol, is one way to mitigate the problems of photon loss in the spin photon gate to establish entanglement. This is just one of many, many schemes that have been developed over the years to entangle two qubits. And you can then repeat that to a third qubit, the fourth qubit, and so forth, and many, many qubits in this kind of a network. Of course, along the way, I want to reuse this electron spin. And if I then want to do this herald entanglement to the next one, I would destroy the quantum information here. So what you can do is make use of some other resources that the color centers provide. Namely, you can do a hyperfine gate, a coupling between the electron spin and a local nuclear spin to swap the state of the electron with the state of the nucleus. And that frees up your electron spin to then broker again an entanglement to the third quantum memory node, and so forth. And that's one way that you can establish entanglement over many nodes. Now, the devil is in the details, of course, and it looks nice on paper, but it's like so many things hard in practice. But actually, using the nitrogen vacancy center, the group of Ronald Hansen has in Delft actually realized a 3-qubit network using such color centers. And moreover, we're able to realize on-demand entanglement, meaning that at any given time, the probability that Alice or Bob at a distance do not have a resource state of at least one belt state shared between them becomes vanishingly small. So that's nice. That's a precondition for scalable networks. So these are big milestone experiments that were done just in the last couple of years. But I wanted to return to this question of how do you measure the utility of a network? So we said sort of hand-wavingly that the utility is chiefly due to these 3 application areas. Can we be more precise? Can we try to put a number to it? So we should, right? We're scientists. And so we should try to make our claims measurable. And so that requires formulating the problem of what is the utility? What is the utility of a thing at all? And so for networks, like I said before, the value of a network, one way to look at it is, well, what's the value of a cell phone network? Well, it's because Alice and Bob, they want to be able to have a conversation. Or, Jim and his grandmother want to be able to send, photos and so forth. So, and they pay for it, right? So if somebody pays for something voluntarily, then that lower bounds the value that they derive from it. If they had less value, yes, personal utility from the good, in this case, the use of the network, then they derive in return, they wouldn't do it. That's the assumption of microeconomics. So by this argument, you can say, all right, should I connect 2 quantum computers by the network that some operator, quantum network, some operator provides? Well, it depends. If the quantum computers could benefit from more qubits, then potentially yes. And if moreover, the network provides links with a fidelity that's sufficiently high that you can run a computation spanning multiple quantum computers, then yes, then the value could be quite large indeed. If you go by the quantum volume definition of the quantum computing value, then it might be exponential with the number of nodes in the network. So actually, it's a strangely it's a very unusual good is quantum computing if you think about it as a microeconomics question. And so I was so interested in formulating and formalizing the problem. And that led us with a team of team members here, including Don Tousley from UMass, and Wen Dai, who maybe not coincidentally is now now works in finance, and Yuan Li, who's an excellent scientist, a master student with me, to try to formulate to try to answer this question that we would often get: what is the value of a core network? And one way to look at it, therefore, is to say, okay, suppose you have these coalitions. Like coalition 1, it comprises of 4 people, operators of quantum computers locally, and they have decided that for them, it's valuable to network them, all right? And they derive some utility increment from a 4-qubit state, or equivalently, some combination of bell pairs, so that they can run a computation non-locally. Then they will pay some amount for the use of that network, and that lower bounds the utility that they have derived from it. And the operator in turn, what the operator does is the quantum network operator, will seek to maximize the aggregate utility of all of these coalitions that the network can service, that can be provided by the network. And so they will say, oh, what coalitions do I sell access to because I have a finite number of bell pairs I can generate per second, and they will do that optimization. And so this is a lower bound this here, the what we call the quantum network utility, on the actual utility derived by some set of people distributed globally, or could be in a data center or whatever. This is a general definition. And then we looked at trying to quantify the different types of applications that are indicated here. And from my understanding right now, the quantum computing is probably the most important of these if you try to quantify the contributions to this, but it doesn't mean that it will stay that way. All right. Okay, so this is one way to quantify this. And oh, there's actually an online simulation tool. This actually was published in PNAS 2024. And there is also an online simulation tool that you should, there we go. So like I said, lots of simulation tool resources for you. So here you can actually go through and run these simulations and ask like, oh, would it be useful for this or would it be useful for that? How big do the collisions have to be for a quantum network to be useful? And I hope that this resource will also be of value to you. And it runs. Okay, so it's a bunch of requirements here. Yeah. Okay, so coming back to this. Now I want to talk about the architecture. That was a protocol question and system level question. Let's talk about the architecture. And here I want to be concrete and share the nodes that we have, give you a sense of like what the Boston area quantum network testbed supported in large part by the Center for Quantum Networks, but also by other entities like MIT Lincoln Laboratory, MIT, by Harvard, by BBN, and by Sandia National Lab, what the network looks like. So here is Cambridge, here's Boston. Let's zoom in to Cambridge. And here we have Harvard, which has in the laboratories of Mikhail Lukin, Professor Lukin, and Professor Marco Lonkar, some set of quantum memory nodes, in this case in dilution refrigerators, one of which was partially supported by the Center for Quantum Networks. And here at MIT, we have other types of quantum memories, and you can see them indicated here. So just to give you a sense of the scale of like one of the leading networks in the States. And so there's some, I don't know, so like a handful or so, maybe a dozen of quantum memory nodes. In this case, just single or a few qubits each that are connected, in this case by optical fiber that run through the ground in dark fiber in the Cambridge area. But Cambridge and Boston area, actually at BU, there's actually also the network actually reaches BU as well. And there are links that are still at the moment too lossy, but hopefully with better protocols and better technology, manageable nonetheless, to MIT Lincoln Laboratory in Lexington, Massachusetts. So this you can, and for that distance, we previously run just purely optical entanglement generation type of protocols. And this gives you sort of a sense of where these quantum networks are at presently. They are in the metro scale. Of course, the desire for some applications, not all, but for some, is that you can bridge longer distances to go between cities and continents and maybe beyond that. However, there are still altogether, there's still many questions on how you should architect this. It's a good place to start to work in for jobs. There's lots and lots of open questions. Even the metro scale, like this is much too small than what you would need, and fidelity is too low. So a lot of research still needs to be done, but it's especially hard when you try to make really long distance links. And that motivated, again, the Center for Quantum Network questions motivated some additional work that actually now led to this midpoint source, a protocol that we're pursuing in the Center for Quantum Networks. So here's just a snapshot of looking at the different resources that are in MIT campus, and you would find at other universities, research universities, you might find similar kind of setups. Here, Carl Bergman and my group and Paolo Capolero, we have these kinds of cryostats that are linked through a fiber network in the campus. Now let's take a look inside of that kind of a cryostat, and what you might see is something like this. This here is a packaged quantum memory node developed by the group of here Ben Dixon, Scott Hamilton, and team at MIT Lincoln Laboratory, Group 67. Very excellent group in photonics and quantum information processing. And so they, together with others at MIT Lincoln Lab, developed these very good photonic integrated circuits based on silicon nitride that have etched into them sockets, little recesses that go through the top cover oxide of the photonic integrated waveguide circuit. And into these, we can place, by, in our case, pick and place stamping methods, small chiplets of diamond. And you can see that chiplet here, kind of an outline in the photograph, and here in the schematic. You see there's 8 waveguides coming out that are connected to 8 diamond memory nodes. And the diamond looks like this. This here is roughly 200 nanometer cross-section waveguide made out of single crystal diamond. I'll show you the fab in a moment. And it's in the socket. And then waveguides of silicon nitride are connected underneath to transfer light from the diamond waveguide into the silicon nitride waveguide. And over here, on these kinds of devices, we often have optical cavities that form a spin photon interface that is enhanced by a cavity, like in cavity QED, to make the spin photon coupling that we showed before more efficient. You need a bunch of other stuff to make these things work, one of which is lots of control of the electron spin ground states and the nuclear spin ground states and the optical transition frequency and so forth. So one of the ways to do that is to apply locally electric fields and magnetic fields. And because you have so many systems, you want to do this electromagnetic ground state manipulation in a way that's scalable, that gives you lots of access points and control. And so for that reason, we set out some time ago with our collaborator, Ronan Han, to develop a branch of CMOS electronics, the kind of electronics that you have in your phone that powers your computer and so on, but now repurposed to this electron spin, nuclear spin, ground state control. And you can see that here, this is a CMOS substrate made by TSMC, and we then transfer our diamond waveguide and cavity structures into it. This slide is old. This was published in Nature in 2024. Yeah, so lots of these technologies have to come together. Some of it is very hard for universities to do, like this beautiful packaging here. And so that's a need for industry. Now let me show you this in this video illustration. So here, suppose this is that quantum memory that we want to entangle at a distance. Here it is illustrated as this red ball, but this is just the electron spin. The nuclear spins, remember, they have to be there also because we have to be able to swap the state of the electron spin to the nuclear spin as part of this entanglement protocol. So here we're assuming that we have 8 of these quantum memories arrayed, and each coupled to a cavity. By the way, this was made by Michael Walsh, who was a PhD student in my group and also quite artistic beyond being a good scientist. And so here what we're showing here in illustration is the optical fields that these optical fields are entangled with electron spins that they leave behind. You could think of it as basically like the brightness or the state of that optical wavefront depends on the state of the electron nuclear spin that was left behind. And then there's a need for routing these, like you want to talk to quantum memory 1, quantum memory 2, etc. Some array of quantum memories, and you want to decide, like, oh, which one do I want to try to entangle, etc. So for this reason, we implement these techniques that are quite common in the telecom wavelength for switches. These are Mach-Zehnder-based switches, but that are not so common in the visible part of the spectrum because the photonic backplanes there are just not so developed. And in this case, we rely on a photonic integrated circuit platform really pioneered by Matt Eichenfeld, who's now a professor at the University of Colorado, and his team at Sandia National Laboratory. And these are the kinds of chips we make in illustration, and they allow you really to combine a lot of optical components so that you can scale these things into what we hope can become really sufficiently controlled systems to be able to distribute this entanglement at the rates and volumes that we need. And so this here is Mark Dong. He's these things, like these chips are really quite small. He's a normal-sized human being, Mark, and they and so we can pack thousands of these memory devices into sort of millimeter scale footprints. And here you see one of the chips that one of the tape outs that comes back from the fab, in this case from Sandia National Laboratories fabrication facility, that they allow like researchers, non-critical researchers like us, to occasionally make use of. And then we get this beautiful photonic integrated circuit, which has these kinds of devices on it. Now, these can switch at some hundreds of megahertz modulation rate. And importantly, for quantum information applications, you can modulate the switching, and all of this stuff has to be done with high precision. And for instance, one question people often ask for using these for atomic systems, quantum memory systems, known as, if you use them for carving out the optical gate, what is the error in repeating like a particular gate many, many times? And for us, the measurement of the intensity is less than 1%. And this is really a controls problem. So I think in some cases we can get less than 0.5%. Extinction ratio in separate experiments, including from QEra, quantum computing company that uses ultra-cold atoms, they've recently set what I think is probably a record in this domain, where they have large numbers, like hundreds of hundreds of modulators with contrast exceeding 40 or so dB each in the visible part of the spectrum. So that's that photonic integrated circuit platform. Sometimes for some applications, you might want to go faster. You might want to modulate faster. And one of these examples is if you want to frequency shift an optical field, one way to do that is to to shift the refractive index of the waveguide that carries the optical field quickly before essentially the optical field leaves the waveguide. And so for this, other materials can be advantageous, and in particular, lithium niobate is one of these. And so here there's a lot of work in building photonic integrated circuit platforms based on thin film lithium niobate. Here's one of our devices. This was published in this was published in Nature Com last year by Ian Kristen, who now works at Berkeley as a postdoc with MJU. Very good prof if you're looking. But this kind of platform was pioneered by Marco Lonkar and his team at Harvard, and is a really useful substrate. Oftentimes you can actually work in the visible part of the spectrum, for example, after you've done frequency conversion. But recently, color centers were discovered in the infrared in silicon, and that has some potential advantages, like you don't have to frequency convert. And so there's increasing interest in controlling large numbers of electromagnetic modes, like optical fields, in silicon. And so here's some of these substrates that we, for example, in my group, develop. This is with AIM Photonics, a research-focused foundry service in the United States, and our collaborators like Mike Fanto at AFRL. Okay, so that's sort of an overview of the photonic layer of the overall technology stack. And we've talked a little bit about the quantum memories already. I just want to finish this one point before we have another short break. So we talked about the nitrogen vacancy center. And if you remember, when we looked at the nitrogen vacancy center, the nitrogen atom was positioned itself to one of the two vacancies that you see here in the diamond crystal lattice. It either is in this site or in that site. This happens at the time of implantation or annealing or so, when it has to make a choice which side it's going to be on. Now, when you take a larger atom, it turns out that the energetically favorable position for it to sit is actually in between. One way to think about this is it gets kind of tight to sit in one of the defects, but there's more room if the electronic orbitals can sort of spread out a little bit if the atomic defect sits in between the two vacancies. And okay, fair enough. So this happens when you substitute the two carbon atoms with one group 4 atom, like silicon, germanium, tin, etc., lead. And it gives you this kind of a center. Okay, now the useful thing about that is that this is inversion symmetric. There is no reason there should be an electron, imbalance on this side versus the other side. And that makes it to first order insensitive because it has no built-in electric dipole moment to electric fields that constantly are fluctuating in a solid and lead, in the case of the nitrogen vacancy center, to a excited state dephasing that makes the atomic transitions broad. So if you use these symmetry protected color centers in diamond, the atomic transitions become narrow and stable, and you can see the numbers here. So you can get to a branching ratio, like most of the light goes into the desired optical transitions, and the line widths of the optical transitions can be very narrow, so narrow that they're largely dominated by just the quantum uncertainty relation of the photon wave packet duration versus the frequency. And you can see that here. This here is showing you the frequency of optical. This is doing photoluminescence excitation spectroscopy. You're scanning a laser across the atomic emitter, and you're looking at the fluorescence collected here in a sideband or from a different direction. And you can see that as the laser comes on resonance with the atom, it starts to emit, and then it becomes dark again. This also, by the way, is spin selective, so this allows you to do your spin selective scattering. And then, of course, you want to look at the features here. So let's take a look at the full width at half maximum. And that line width has this uncertainty relation with delta omega times delta t. Has to be greater than or equal to 1. And that comes out for the lifetime of a tin vacancy emitter, which is about 4 nanoseconds. Once you've excited it, it takes about 4 nanoseconds. So the wave packet is about 4 nanoseconds. And if you plug that into the uncertainty relation, you'll get that the line width here ought to be about 20 megahertz or so. And in experiments, we see that for tin vacancy centers, we can come quite close to that line width. And you can see that here. So here is the line width measurement, and there's a spread of the atomic transitions, but the line widths themselves, you can see here a histogram of these kinds of measurements. This is for silicon vacancy center, which has a roughly 3 times faster decay time, so the line width is 3 times larger. So take 20 megahertz times 3, 60. So this here would be line width limited. This is the best as you could possibly do around here. And you see that they're a little bit worse, but not much worse than the quantum limited line width allows. Okay, so, but still not good enough. You see, this is one example of the many outstanding problems with color centers or any kinds of solid state emitters for quantum memory applications, is that there is some additional noise that immediately will affect your coherence, your gate fidelities of this distributed entanglement experiment. And there's different ways that people deal with that. One is by filtering. So you can filter and then you trade fidelity against success rate. Or you use variations of entanglement schemes, and we'll get back to that in a moment. I want to just mention in passing that this is also quite an interesting system, these color centers in diamond, for many other areas of science like microscopy And recently, for example, we showed, and this is a paper that appeared in Nature Communications last year, people who are interested, that it's kind of interesting. You can actually see the discretization of the atomic lattice in an optical experiment. So you can see the atomic scale in an optical experiment come if you have stable measurements for long enough time, and that gives you a violation of the conventional 1/square root of n scaling law. So look at that paper if you want to know more. Now, fabricating these devices from these kinds of diamond substrates is actually it's a difficult process, and a lot of unknowns remain there. As you see, we're like from the properties of the emitters, we're not good enough yet. But so here I just give you a sense of what this entails. One way is to first you get a diamond. Oftentimes these are grown by chemical vapor deposition. You do low temperature microscopy. You do spectroscopy on the quantum emitters. Here's an emitter, here's another emitter. You look at the line widths of these, and then you can fabricate structures in the clean room out of them. Why would you do that? One reason is that this is one way to mitigate this problem here, right? We want all of the emitters to have a line width around 60 megahertz, but the majority of them have a line width that's greater than that. So we don't want that. So one way to solve that problem is to use the physics of cavity quantum electrodynamics, where if we put an emitter inside of a cavity, we can increase the vacuum fluctuations of the electromagnetic field, the ground state fluctuations from a quantum harmonic oscillator, and thus encourage the atom to decay faster. So this is called the Purcell effect. And when you decay faster, that means your radiative quantum limited line width becomes broader, and you can shift what are naturally not so good emitters into into a regime where they are good. In particular, what this would mean is that the line width of emitters radiatively limited, quantum mechanically, would be more here, like 400 megahertz or so. Now, if you have this additional broadening, whatever gave rise to this spread here, eventually that can be sort of, becomes negligible if you have sufficiently high Purcell factor. And that's one of that's probably the chief way to deal with this problem at the moment. Here I have some information on how, like, let's look at the spectroscopy of one of these color centers. Now these are group 4 vacancy centers, and in particular, tin vacancy has emerged as really one of the leading systems, tin and silicon probably. And here is what the spectroscopy looks like. So here we have one of these photonic integrated circuits from MIT Lincoln Laboratory that I showed a little while ago. Here's the diamond chiplet. We have an optical fiber array that couples light to a diamond waveguide. And inside the waveguide, we have color centers. In this case, these are 10 vacancy color centers. Here we have the ground state hyperfine levels that correspond to configurations of the electron and nuclear spins in the ground state orbitals of the color center around the host nucleus. And then we drive optical transitions, and you can see then this optical spectroscopy. So this is what these kinds of experiments look like. And here we see that if we do dynamical decoupling to decouple the ground state electron spin coherence from slowly varying magnetic fields, this is a conventional method from NMR, then we can increase the coherence time to some milliseconds or so at a temperature of about 1.5 or so Kelvin. We expect that at lower temperature, this should get much better, but the measurements are underway. So here's what this electron spin nuclear system looks like. Now, you need this broker qubit. Now, there I showed in the beginning with a nitrogen vacancy center, I just showed you one spin, but it turns out it's actually in the NV system, it's actually 2 spins, and you use a spin triplet, the spin triplet manifold, as the quantum memory. That thing is sensitive to stray electric fields. So now we go to group 4 vacancy centers, and there the leading systems are spin 1/2 ground states, not spin 1. And And here you have, well, an electron spin, but it's also coupled to the nuclear spin. So you have to basically be careful about how you actually want to encode your quantum information into the ground state of this set of electron and nuclear spins. That's my point. You have possibly many electrons, like one or two, maybe three, if there's a nearby electron spin, plus one or more nuclear spins that are at play. So it's a whole set of magnetically coupled spin systems. And your charge as a quantum memory expert would be find me a good embedding of quantum information as a memory and quantum information that's not a memory necessarily, but talks well to an optical field. And that second type we call the broker qubit. So you want to have a good broker qubit that couples to an optical field, and then a good memory qubit that is not coupled to the optical field. And this is sort of the exercise of this paper here. But the point is that we try to do what we said at the beginning of the course. We try to broker entanglement and herald it with high fidelity so that we have this resource by which we can subsequently teleport quantum states or gates between multiple qubits. And I'm sort of flipping through here the setup and give you sort of, yeah, this is sort of state of the art in the field, like several milliseconds of spin coherence time. Here's the coherence time of the broker qubit, which again is going to be lower because it couples to the optical field. And you control this by gate control pulses. And I talked earlier about the quantum memory integration into silicon CMOS, so I won't do that again. But I did want to mention that, yes, so in silicon, in fact, it has been discovered, not by us actually, but by the Simmons group, for example, at the University of Vancouver, British Columbia, that like silicon itself is host to promising color centers that also have optical transitions, like the diamond color centers here, and you can tune these. And so here for example, we in my group, there's some work ongoing in coupling these kinds of atomic memories into these large-scale silicon photonic integrated circuits. All right, so this gets me to the overview of quantum memories, how they look inside the cryostat and how the cryostats are connected. And I think at this point, I want to again take a short break, 5 minutes, and then we have the last thing is just going to be 20 minutes after that, and at which point we will go into the simulation environments. So here I'm happy to take questions if people would like, and we'll take a short break here.
Great. So in the Q&A box, there's someone asking, is there any particular reason why group 4 color centers in diamond are preferred over other defects in other solid state materials, such like defects in HBN or silicon carbide?
Yeah, there are reasons. So the question is there a particular reason why like diamond would be a better host?
Mm-hmm.
Yeah, that's a good question. We should always ask that. Diamond is a favorable host for a couple of reasons. One is you want your memory to be in a environment that's well isolated from fluctuations. So well isolated environment. And so let's take a look at, so we talked already about electron spins, the electric fields. So diamond has so if you want low fluctuations in electric fields that couple to the atomic transitions, the atomic properties that are connected to your qubit. So one way to do that, and then very important thing is to be away from surfaces. Surfaces have fluctuating charges and are difficult to control, and thus have greater electric field fluctuations than if you're further away from surfaces. So that is an argument in favor of three-dimensional materials compared to two-dimensional materials, uh, uh, where you're close to many surfaces. Now, okay, van der Waals materials, you could say surfaces are stacked on top of one another, but the defect density in stacked materials is substantially higher than in 3D crystals like diamond. So you want to have a low defect density, and you want to be away basically from origins of fluctuations in electric fields. What about other things? What about magnetic fields? Okay, let's see. In an atomic lattice, where do the magnetic field fluctuations come from? Uh, uh, one microscopic origin is just the fluctuations of other spins in your surrounding um, fluctuating, um, and and so and you do what you can, and in the end, the thing that you can't control is or very difficult to control is the fluctuation due to residual nuclear spins in a crystal. Okay, if you're in a crystal lattice where every nuclear spin, you naturally choose ones where the electron clouds are filled in such a way that the the magnetic field is balanced between electrons in the outer shells. So that's a precondition. Then you're still left with the nuclear spins, and the nuclear spins will fluctuate. And so you'd want to have a material that has ideally no fluctuation, which can be done by having a material with no nuclear spin. And if you look at the periodic table, the group 4 has atoms that have a large abundance of spin-free nuclei. For diamond, carbon, the abundance is like 97% or so, or not magnetic. Do not give a magnetic field. And you can furthermore isotopically purify the material to make a magnetically quiet environment. So then you have electric and magnetically quiet environments. Next up, how else do you couple to the lattice? Phonons is one. And here you want a crystal that's very stiff, because that means at a given temperature, if it's very stiff, the phonon occupation probability, given also by the Bose-Einstein distribution that we looked at a moment ago, is small. And so you want small phonon you want to minimize phonon scattering, and so forth. And you can go down the list, and one after the other. Diamond, if you were to put these on sort of like an axis of good and bad, diamond tends to fall on the good side. And it's really the combination of many, many good things that make diamond special. The combination of simultaneously achieving these sort of check marks. There's some things that in diamond are not so favorable. One of them is the fabrication is difficult. But thus far, it's a good trade-off.
Thanks, Dirk, for answering this and adding a lot of necessary informations about the current progress. Okay. Any other questions from the audience?
Yeah. Oh, hey, can you take it elsewhere? Yeah, I have a course. Okay, thanks.
I still have some poll answers if you guys want me to read through those.
Yes, very great. Yeah.
Okay, Enrique says, I'm from Peru and I'm studying software engineering and I haven't graduated yet. Another person put PhD student in Madrid with research on QEC. Another person said, master student in computer engineering, UMD, College Park, exploring research area in quantum information processing. I had somebody else from Hawaii say, I'm a first-year PhD student in electrical and computer engineering at University of Hawaii at Manoa. I have another person says, I have currently enrolled in Master of Physics program and experience with IBM QuizKit and Penny Lane models to solve real-world problems integrating quantum machine learning and chemistry. Aaron said, PhD student working in ion trap quantum computing at the University of Oxford, focusing on networking experiments.
Oh, okay.
Student said, hello, grad student in CS and engineering, really interested in quantum. Thank you so much for all these resources you have made for us. Really looking forward to going over them. Another person said, I am from Connecticut. I am studying a master's in optical science at the University of Arizona, and I did my bachelor's in physics at UMass. And Adrian says, hello, I am Adrian. I am based at UCLA working in computational medicine, specific cardiology and cardiovascular disease research. I am working on my PhD. Hi, I'm
Wow.
Hi, I'm Alexander from Peru, currently studying computer science. Another person said, I am an electrical engineer studying for a doctoral degree in mathematics. And finally, somebody said, master's in data science, applied AI, working towards quantum ML.
Wonderful. Okay, super. Thank you for sharing that. And some
No
connections are made
problem.
between you all directly. And Adrian is Adrian is the UCLA researcher in cardiovascular. Right? So apropos cardiovascular problems, you can get cardiovascular problems if you look at the zoo of entanglement protocols that have existed, that have been developed for doing what we were talking about a moment ago. So we talked about the Barrett and Koch scheme, but there's really a litany of different kinds of schemes. Like you could do two photons in this way. You can do off-resonance scattering. You can do single photon, but at a loss of potentially fidelity or rate. And so there's really there's a whole zoo of entanglement protocols for stationary qubits with photonic interfaces, like the atomic transitions of these atomic defect states. And so we always felt like we growing up with in this field that there ought to be some taxonomy, uh, sort of like to categorize all these different ways of entanglement distribution with stationary qubits with spin photon interfaces. And and that led us to write a tutorial that I want to just get to here. Remote entanglement protocols for stationary qubits with photonic interfaces. So this here led to a code base called QREB that is available on GitHub. And I think it's quite good. And it's a method to compose quantum protocols and quantum entanglement distribution protocols by some set of elementary blocks. So this was completely accidental, but I happen to have a little Lego piece here. And Legos are amazing. You can do all kinds of different things out of pretty small set of elementary building blocks out of Legos. And our motivation was the same here. So what are the elementary building blocks that you need to construct this zoo of entanglement protocols? So you need a spin photon interface, some interaction between spins and optical fields, between atoms and optical fields. You need beam splitters we talked about, right? What else did we talk about? Photodetectors. And so some set, it's about 20 or so of blocks allow you to compose the entirety of quantum entanglement distribution protocols. And so we built these little code blocks for the components and then arranged them to rebuild the way people do these different schemes that are this litany of papers that you're not supposed to read because it's confusing. But once you have some Lego alphabet, you can you can replicate all of these things out of this set of building blocks. And so here's an illustration from this composable platform for entanglement generation. And I want to actually now show you what this looks like, and we can actually go through an example. So there exist logical building blocks. These include the circuit diagram here. This is what I showed towards the beginning of the course, where we have two electron spin systems. They're initialized. Let's say I initially had 0, 0. In this notation, you could say plus, plus, different bases. And then you want to generate entanglement between them. One way to do it is a C naught, but if you don't have a C naught, you can construct one in a heralded way by using two ancilla qubits. These ancilla qubits here are optical fields, also initialized in a known initial state. This is the laser field, for instance. We know what the laser field is. It's an initial known state. It's a particular state of the electromagnetic field. And we interacted with the qubit after, in this case, actually, it's gone through a Hadamard gate. And then we we do a joint measurement on the ancilla qubits coming from Alice and Bob in a Bell state measurement apparatus. Now, this Bell state measurement apparatus in itself has to be constructed, and you would want an apparatus that can distinguish between all four Bell states that we talked about, but it's really difficult to do with linear optics alone. It's impossible, actually. But you could use linear optics, but it's very difficult to do. So you kind of but you can do it half of the time. So if you set it up, you can get perfect measurements half of the time. And this is the linear optics Bell measurement allows you to do that. And so, and that's actually done by just a beam splitter and photodetectors, for photodetectors. And you can, in the framework of this QREP, you can construct that linear optics Bell measurement. All right, now you have the ingredients necessary to simulate this type of protocol, and you can rearrange these parts to do other kinds of protocols. So here's spin photon emission and so forth. So rather than looking at this slide for too long, I thought we would actually go through an example. So here, I'm going to go here. And so let's go to this. And now let's look at some of these notes. So I want to just give you sort of an overview of the notes and then actually jump into that, that notebook in particular. Quantum mechanics, QKD. All right. So what you will find there is resources for, and I will have to do this. We're going to run out of time. I will send you an email once this material is incorporated into the interface that I shared with you that has the interpreter, and you'll have to go back to it then and use it then. We're going to run out of time to actually do this live, I think. So here you have, so this is just a review of the, oh, actually, yeah, sorry. So, so here is the kind of protocol that I was talking about a moment ago. So you have, here's the linear optics Bell measurement. You know what? I think we will run out of time. So I'm gonna just give you a sense of what's in these notebooks. So in this notebook, you have a simulation I put together for quantum key distribution. And one way to do quantum key distribution is with, I mean, the best, really fundamentally, the reason why it's secure is because of the non-locality of physics. And so this goes through different kinds of quantum key distribution protocols like BB84 in a sort of illustrative way. We don't have time to get through this. Many of you have seen this before. The midpoint source protocol for quantum links is quite useful. And I would want to do that also, I think, interactively. Here is the QREB scheme. And so, yeah, this is the modular theoretical framework for like the, for understanding photon-mediated entanglement protocols. And so to get this started, you can download QReb from this repo here. Actually, do people see my, yeah, you should see my whole thing, right? So the repo is here. I'm going to share it. If you want to just download it locally. But let's see what's inside and look at some examples. So you can do this with pip install. And it presents you with the logical building blocks that we just looked at a moment ago. These are the logical building blocks. Here's, you can, the spin photon interactions. Here is spin blocks themselves. So you could ask, for example, how, like, construct a 6 pulse dynamic decoupling sequence in QReb. Give me the code. All right, while chat tutor is thinking, we can move on. Here's how to set up different kinds of encodings. You can do encoding in the number state basis, in the computational qubit encoding for optical fields. Could be number state, could be time bin, it can be polarization, it can be dual rail, it can be frequency based. And these all have trade-offs. This is why there's this big zoo of different protocols. And really to evaluate what is the best protocol for your application, I can think of there is no better way than to take the assumptions to take the assumptions and which encodes the knowledge that you have about your system, including what you want to do with it, but also what is the spin coherence time? What is the dephasing in your environment? Like if somebody talked about HBN, right? Like what is the magnetic noise in that system? And encode it into a digital twin, encode it into a simulation for that system that you're studying. And then you can use a tool like QReb to say, all right, can we explore, the combinatorial complexity of different protocols and encoding types to minimize the cost function of, let's say, gate error. That's the best way I know how to answer these kinds of questions that are often put to me. What's the best scheme for this and this? There is no answer. It really depends. And it depends on your assumptions, depends on the system you have. And the way to answer that, the best way to answer that now is really, thanks, AI really helps you a lot. You see here, as we were talking, Chat Tutor has built us a Python script that imports this Q-tip, right? And imports these pulse sequences that you can then apply for one way to do the 6 pulse dynamic decoupling called the CPMG sequence. Okay, and then you would apply that to your system. Now, suppose that my qubit system is let's assume here that it's a spin 1/2 is a spin 1 NV ground state rewrite. And in the other resource that I shared with you, you can actually it's basically the other thing I shared with you is like a ChatGPT, but I can actually execute Q-tip. Very satisfying that ChatGPT will execute Q-tip for you in its environment, and that does that. And when I've just fixed the permissions there, you will be able to do that. Yeah, and so you can explore with this resource of physics-based models. You can explore the different ways of compiling the quantum control functions into onto the physical space that you're working with. What should it be? Like Fox state encoding, time band encoding, and so forth. And here are the different types of protocols that you can express this way. Spin operations. You see, it's quite a long set of resources here for you. Here's a summary of the building blocks of the quantum channel. And here are the kinds of calculations that you can then do, estimating like things like success probability per attempt for protocol A, B, C, etc. What about protocol C together with WCS and so forth? Incredibly difficult to do the conventional way because combinatorial explosion of ways of doing stuff, but you can explore it with automation much more successfully. And I should say actually along the way I'm really fascinated by the possibilities of using agentic AI and so on to explore these kinds of questions that have nagged me as a PI on large research programs, since forever, since I started my faculty career, honestly, even as a grad student. I would say, why are we doing it this way? Yeah, because we don't know the other way. We're kind of doing it, it's the best guess we have, right? But it leaves a bit dissatisfied. And so for me, this is really exciting that we can just look into a lot more directions. And if people are as excited about this somewhere as I am, I also would say I welcome people to write me if you want to get involved in building these AI-based models, which allow also, here's another example, like you want to have good instrument models. Building a good instrument model, this was done by a postdoc of mine, Young Hu, in collaboration with some collaborators here, Chaim Shukovsky, for example, at Tel Aviv University. And they founded a company called 3D Optics that's enabling this very good tool. But this still takes a very long time. And generative AI allows us, or agentic AI, these kinds of tools allow us to build this kind of thing. Now, not at the complexity that we have here, but it's getting better. And the biggest problem in the whole chain in building these kinds of models is the verification. Like when you did something, how do you know it was done not incorrectly, right? How do you know it didn't violate some rule? And this is actually why along the way, I was inspired to found a company with collaborators of mine, Marin Soljacic at MIT, Frank Coppens at ICFO, Alanas Paraguzik at Toronto University, and Joyce Poon at Toronto University, and Amir Gadimi of Litium, to start this company. This is an old slide. So this company is underway. You can take a look, Axiomatic AI, and it actually gives you access to some of these kinds of models and the ability to extract models from research papers. And much of the material I showed you here was actually extracted from papers by AI with verification. So using mathematics-based reasoning to check if AI is doing the right thing, using a tool here at I guess I could bring it up for just at the very end here. So this thing, if you want to play around, this allows you to build these kinds of models. And yeah, you can upload a paper and try to extract from it a model, and the kinds of models that I was showing you here are derived in that way. A combination of math-based, verification with physics knowledge. All right, this brings me to the end of my slides. Pretty much to the end of my slides. Along the way, I should say, axiomatic is really for me the thing that kind of ties a lot of the other efforts in entrepreneurship together. This comes about because there are big opportunities, but also big challenges. And actually, particularly relevant for quantum networking is a company called QNet that's doing some really cool stuff. You can check them out. And QEra I mentioned earlier today. So with this, I thank you for your time. And like I said, I will be in touch about giving you access to the quantum simulation framework. But I'm encouraged also by our leadership to ask you for a course evaluation. So you'll see this timing here in this course was not ideal. And but it turns out that despite the AI tools, it was actually, I will say, incredible amount of work to put these brand new slides together, these brand new resources together. And I really do hope that they will be useful. And I would much appreciate any positive or negative, any sort of feedback that makes it more fun, really, to put these kinds of resources together for people interested in my field. Thanks very much.
Great, thanks, Dirk. I just want to add a point is like if you have a subject you really want to dive into and generating a really good notebook, feel free to send to us and Dirk can putting that together with Chat Tutor.
Yeah, that's right.
Yes, and thank you everybody for attending today. Thank you so much, Dirk, for your presentation. Thank you, Chauhan, for assisting with that. And if there's still people in the room right now, feel free to reach out to our instructors if you guys are curious about anything, have any questions, and want to hear more resources. But yeah, thank you guys so much.
Thank you. I will say I'm bad with email. I spend too much time making these kinds of resources and stuff like this. So yeah, if you contact me, I'd love to hear from you. Just one question that you CC my admin, Janice Pelzer.
And Dirk, do you want the email everybody to contact you at, your MIT email?
Yeah, that's a deal. It's actually shared with Janice, but nonetheless, it would be good to copy
Okay.
Janice. So if you don't get a response, it's yeah, it's not because I will have missed it, but I really love to hear from people,
Yeah.
and Janice makes it more certain that I will.
Yes, I will drop those in the chat for everybody. So if everybody has time to take a quick screenshot or save this.
So the Janice email is
Yeah, sorry. Just I hate to put her email here because she's also, but you can just copy her. Just copy, like direct
yeah.
at me, but copy Janice. Okay, I assume people are typing away furiously with chat tutor or something, or fully engrossed in the QRub.
Hmm.
Good. I mean we're at the 2 hour mark, so or do you normally leave some time for discussion there at the end?
Um, yeah, if anybody has any questions, feel free to drop them in the Q&A box. If not, we can go ahead and end the Zoom call.
We can leave like 5 minutes then.
Yeah, we'll just do what is it over there? 5:10.
Mm-hmm.
Okay.
It looks like we have a question in the Q&A box.
Mm-hmm.
All right.
What's the number of samples measured in silicon vacancy zero Fano line transitions?
The number of
I guess it's meaning that when you measure the zero Fano line, it has a spectral diffusion, right? You remember the
yeah.
Marcos group, they measure that? I think probably around 100
Oh,
samples.
in silicon vacancies?
Yeah.
See? Oh yeah. Um, I think in the paper that I shared there, this is Madi Sutula, 2023 Nature Materials. Silicon vacancy centers, we probably measured a few thousand, I think. Oh, yeah, I said like because we did parallel measurements and that's very useful. That like the statistics are super important, and you have to. That's another area where this field has to grow is in statistical metrology. We could share that paper if that person doesn't find it.
Mm. Yeah, and silicon vacancy has a spectral diffusion, which means different samples may have a slight different zero photon line and emits different photon wavelengths. Yeah.
Yeah.
Okay, it looks like we've reached 5:10 and we haven't received any more Q&A questions. Is there any final remarks from either of you?
I think we are good.
Okay, sweet. Thank you guys so much again for doing this webinar.
Okay,
Absolutely.
great.
Good. All right.
Have a
Have a
good
good
weekend,
weekend.
everyone.
All right. Goodbye.
Bye, everybody.